All right, this is AP BC Calculus. We're doing a BC only unit. This is Unit 10, Section 10, Alternating Series Error Bound. So just a quick review of the alternating series test for convergence. We've already seen this. So if a series meets this alternating series test for convergence, which basically hinges on two things, right? The b sub n, which is the positive part of the series, is decreasing, and the b sub n is going to 0 as n gets really big. If those two things are true and a series converges, we can use the alternating series error bound to find the error of the series. So basically, the terms of partial sums of a series that is alternating will jump back and forth because the numbers alternate between positive and negative, right? So for example, right, if we just let's say that we are trying to find the value of the infinite sum. Let's do -1 to the n 1 over n, and we'll do -1 to the n minus 1, right? So we'll start at n is 1, and we'll go to infinity. And so this is the alternating harmonic series, right? So this would be a 1, and then a -1/2, and then a +1/3, and then a -1/4, and et cetera, et cetera, et cetera. Okay, so what's going to happen is that if I wanted to find this infinite sum, right? So the sum of the first term is just a 1, right? But the sum of the second term would be smaller than that because I'm subtracting, right? So it would be a 1/2. But then the sum of the next one is going to be bigger than the value I just got because now I'm adding a third, right? So now it'd be this plus a third, right? Which is essentially going to be the positive 1/2 that I just had plus a third. So see how it gets smaller and then it gets bigger again because I'm adding a third, right? Let's see, that would be 5, 6, right? And then it's going to get smaller because for S4, I'm now subtracting again, right? So 1 minus a half plus a third, which is what I had before, but minus a fourth. So see how it gets smaller. So see how the sum is dancing around a number, right? So this value is, and you can kind of see this if you were to look at these values, right? So here's, let's call this 1, and here's -1, right? Okay, so the idea is that just the sum of the first terms, right? When I plugged in, it was a 1, right? But then the sum when I plugged in s sub 2, right? So the sum was a half, right? So here's a half, right? So the number was here, it got smaller, right? Then it's going to get larger again, right? When I plug in 3, it's going to be 5, 6, which is like here. And then when I plug in 4, it's going to be here. So what it's doing is it's like dancing around this actual sum. Like, let's just pretend that this is the quantity s. So the number is higher than s, but then I subtracted something, so it's lower than s, and then it's above s, and then below s, and then it's going to keep getting closer and closer to s as we get to infinity, right? But it's going to keep bouncing back and forth. Okay, so all of that to say that the error between the actual sum, right, the actual sum, which we're going to call s, and my approximation, which we're going to call s sub n, it has to be smaller than whatever the next term in the series is, because think about it this way. The error between this and the actual value, right, it has to be smaller than this jump, right? Because I know that I'm jumping across the line. So whatever quantity, whatever amount I get here, I'm jumping across the line. So this amount, right, this a sub n plus 1, has to be bigger than the error, which would be the distance from here to here, right? So see how this quantity, right, this red amount, has to be bigger than the green amount, because the green amount is my error, right? And then let me, for argument's sake, this amount is the distance between the a sub nth term and the a sub nth plus 1 term, right? So it has to be smaller, right? Then, I'm sorry, this is the amount I'm adding. So the purple, right? That purple right here, that's my a sub n plus 1. It's the difference, right? So that's the idea, is that if you have an alternating series, because the sum is going to oscillate back and forth until it converges to whatever that s is, the next term that you're not using always has to be bigger than whatever the error is in your calculation. So we can see that this thing converges using the alternating series test, because remember, this is a -1 to the n plus 1. That's the part that's alternating, right? And that means my b sub n is a 4 over n squared, which definitely converges because it's a p series where p is 2. So if it converges without alternating, it definitely also converges by alternating. But sure enough, b sub n is decreasing, right? And b sub n is definitely going to 0 as your n gets infinitely large. So it definitely works. That means that the error, right? So we're going to determine the smallest value of k such that the kth partial sum is within 1/100th of the actual sum. So here's the idea. What that's saying is the actual sum minus s sub k is less than or equal to 1/100th. basically what that's asking is that's saying that this is the a sub k plus 1th term. That's what's happening here. We're saying like using alternating series error bound. So a sub k plus 1 would be negative 1. I don't really need the negative 1 because it's in an absolute value, right? So this is the absolute value of a sub k plus 1. So I have a negative 1 to the k minus 1, but I recognize that it's in an absolute value, so I don't care. Over a 4, and then a k plus 1 to the second, right? That would be the k plus 1th term. So we're basically saying that 1 over 100 equals 4 over k plus 1 quantity squared, right? So if I cross multiply, I get k plus 1 quantity squared equals 400, right? So k plus 1 is equal to plus or minus the square root of 400. So technically, k plus 1 is equal to plus or minus a 20, but you can't really have a negative 20 because k is a counting number. So while it technically is true that this is a plus or minus, k is a counting number, right, or a natural number. So k is not negative, right? You can't have a negative counting number. So we're saying that k plus 1 is equal to 20. We're looking for k is equal to 19. So I would have to go 19 terms to get the error of this series to be within 1 over 100 of the actual sum. So again, what we're saying here is it's an alternating series, so the error has to be within, right, has to be within 1 over 100. Well, that's the same, the error is the same as whatever the next term is. So if I want the k terms in the sum, then I look at k plus 1, and that's the idea of how alternating series error bound works. Same idea, right? This is definitely an alternating series, right? This is the part that alternates. The b sub n is 1 over n cubed, which definitely is decreasing as the n values get bigger. Sure enough, the denominator will get bigger, which means the fraction gets smaller. And b sub n also goes to 0 when you plug in infinitely large values of n. So this converges by the alternating series test, which means that the difference between the actual value of the sum and the kth approximation, like adding the first k terms, should be less than or equal to whatever a sub k plus 1 is. But they're telling me that they want that to be a 1 over 1,000. So I'm just going to say that a sub k plus 1, which is the negative 1 to the k plus 1 minus 1. But again, I don't care because it's in an absolute value, right? With a 1 over a k plus 1 quantity cubed has to be equal to the 1 over 1,000, right? That's my 1 over 1,000. So 1 over k plus 1 cubed equals 1 over 1,000. 1,000 equals k plus 1 quantity cubed. If I cube root both sides, I get 10 is k plus 1, so it seems like I'm looking for the 9th term. Right, so I need the sum of the first 9 terms to get within 1/1000. All right, let's try another one. So again, we can see that this is alternating, right? That's the negative 1 to the n plus 1. And then my b sub n term is a 1 over n to the 4th, which definitely is decreasing and definitely approaches 0. So I can go ahead and apply the error test. So we want the smallest value of k such that the difference between s of k, or sk rather, and s is less than or equal to this 0.0001, right? I don't really need the negative 1 because of the absolute value, right? Because that's going to get knocked out, and this is a k plus 1 to the 4th. So I want this thing to equal this thing. Well, 1 over k plus 1 to the 4th equals, so this is tenths, hundredths, thousandths, 10,000ths. So basically, we're in the same situation where when I cross multiply, I get 10,000 equals k plus 1 to the 4th. Now, I've been conveniently picking powers of 10, but if I square root this, technically this is plus or minus, sorry, not square root, 4th root. If I plus or minus, I need a plus or minus because it's an even root, rather, right? But I don't really because k can't be negative. So, so in this case, k can't be a negative value, so I'm going to get 10 equals k plus 1, because that would be 10 to the 4th. So I get another k is 9. And again, there is definitely a trend here. They're not always going to be 10s, but that's kind of the gist. All right, so last one, right? So this is we've actually seen this. This is definitely the alternating harmonic. It definitely converges. So again, if you need to see it this way, right? So my b sub n is just 1 over n, which is definitely decreasing and definitely approaching 0, right? So I can do the alternating series test, which means the sum of the first k terms, the difference, that's the error, right? This is the actual sum minus the k terms, should be less than or equal to whatever a sub k plus 1 is, right? So I want the absolute value of this negative 1 to the k plus 1, which again doesn't matter because it's an absolute value over k plus 1, right? That should be equal to 1 over 1,000, right? Because this is tens, hundreds, thousands. So basically, I want k plus 1 to equal 1,000 when I cross multiply, so k is 999. I would really have to go pretty far to get an accurate approximation for this. All right. And that's basically how it works. Now, I did conveniently pick values that were like 0.001 that were, powers of 10, but it doesn't have to be a power of 10, right? I could have made you find when this thing has an error that is smaller than, I don't know, 1/8, right? So just to show you as one more additional example, like let's say instead I'd given you the same one from 1 to infinity like this, and I asked you for error less than 1/8, for instance, right? Well, then it would be that the error, which is the actual sum minus the sum of the however many partial terms, right, which is a sub k plus 1, right, that thing would be equal to 1/8. So essentially that would end up being a 1 over n. The absolute value knocks out the negative 1 part, 1 over n plus 1. The absolute value knocks out the negative 1 part, right? So I would just end up getting that n plus 1 was equal to 8, meaning I would need 7 terms to be that accurate. So it doesn't always have to be a power of 10. I just conveniently picked some powers of 10. And that's it for our alternating error bound.